set up, so I want to make sure that I am speaking properly. And I think so. Okay, cool. So I can drag this out of here. Let's see, is this? This just shows part of it. Okay, cool. So I wanted to revisit stoichiometry. I just want to write because I don't think it didn't save, and I wanted to be able to submit this onto YouTube. So stoichiometry, and ooh, this unit is particularly useful for determining determines yield of products. It determines quantities of your reactants. And you can use stoichiometry in a lab when you're doing research or when you're doing your undergraduate lab experiments, because you can use this to minimize unwanted products in order to make sure that you're not getting something that you don't want to get. If some side reaction is going to give you a product you don't want, use stoichiometry, you make a certain amount of something that can only make a certain amount of your unwanted product. I do think that stoichiometry is a quite difficult topic to learn. So I think the first thing we'll do are steps to find limiting reagent. Okay, still, okay. So the first thing you're going to want to do is you want to write out a balanced equation. And let's say we have an equation like this. We have iron solid plus oxygen gas gives us Fe2O3. This is known as rust. And the first thing we want to do is we want to balance the equation. So this is unbalanced. And we can tell easily because we have one iron here and two irons here. So there are multiple ways to do this. You can either start recognizing inequalities and sort of bounce back and forth, or you can solve this as a system of equations. And personally, I use my own chemical intuition and I just sort of balance one way, balance the other, bounce back and forth. So the first thing I'll notice is that we have 2 iron over here, 3 oxygen over here. Might also be nice to assign oxidation states. So if this is 2 minus, this becomes 3 plus. So it's ferric oxide. This is 0. This is 0. So the first thing I'm going to do is I'm going to notice that this should have a 2 here. So if I put a 2 here, I just balanced my iron, but I didn't balance my oxygen. So I have 2 oxygen on the left side, 3 oxygen on the right side. So the easiest way I know to do that is the lowest common multiple of 2 and 3 is 6. So if I make this to be 6, so I see O2 not balanced. So find lowest common multiple of O2, O3. This is 6. So the only way I can do that is if I multiply this side by 2 and multiply this by 3. So I'll rewrite this part, Fe solid plus 3O2, 2 Fe2O3. The only thing I notice on this side is that I have 2 iron on the left, 4 iron on the right. So the quick fix to that is just putting a 4 up front. Oops, maybe that. And you can check this and make sure that it's your lowest whole numbers because I can't find a common denominator between 4, 3, and 2. So this is the lowest coefficients that would allow this to be balanced. So let's get a new page. So now that we have our balanced equation for Fe3 oxygen, side. So balanced, let's put a check here. So now let's move on to step 2. And that's convert everything to moles. So let's say, example, I have 15 grams of iron and 48 grams of oxygen. And the goal of this is to figure out how much of your product you're making. So I need to go to use your periodic table. And more specifically, molar masses. So I'm going to quickly look at mine actually. And I find that iron's molar mass is 55.85, oxygen is 16. .85 grams, and that's per 1 mole. Oxygen, 16.00 grams, and this is for 1 mole. But it's O2. So if I have O2, O2 has 2 times 16 grams per mole equals 32 grams per mole. So it's 15 grams and 48 grams. Let's go to the next page. It's iron. And 48 grams oxygen. And I know that this has 32 grams per mole. And this was 55.85. And let's keep this equation over here. Okay, so now that I know how many grams are in 1 mole, I have to find how many grams are in, or how many moles are in 15 grams and 48 grams of iron and oxygen, respectively. So let's find moles oxygen first, because I think I don't have to use my calculator for this. And that is written in as 48 grams O2, and this is over 1. Now I want to cancel out my gram units, so grams have to go in the denominator, 32 grams. This is in 1 mole. My grams cancel. And what I'm left with is 48 divided by 32, and that's going to be in units of moles oxygen. 48 divided by 32 is 1.5, so I have 1.5 moles of oxygen. Now if I look at moles iron, this is 55.85 grams in 1 mole. And I have so I wrote this the opposite way. I want to keep it consistent, even though the units will cancel. So I have 15 grams of iron over 1 times 1 mole of iron is in 55.85 grams of iron. So grams of iron cancel out, grams of iron cancel out. I'm left with moles of iron. 15 divided by 15 is probably just under a quarter, or just over a quarter, or just under a quarter. So it's 15 divided by 55.85. 0.267. I'll just round to 2 sig figs, so 0.27. 0.27 moles iron. So right away you might get an inkling to determine iron is automatically the limiting reagent just because you have less than this. But there's one step before that, and that is the mole ratio. And this is governed from balanced equation. So if my balanced equation is wrong, this step might be wrong. And this is why it's important to balance your equation. So I have 4Fe plus 3O2. And I need to see the ratio of moles of iron versus moles of oxygen that give me moles of my product. And so what I can see here is that for every 4 moles iron, it's going to be equivalent to 3 moles of O2 as far as facilitating this reaction. So let me get a new page and remember 1.5.27. 1.5 moles O2, 0.27 moles iron. Write this equation out for the 4th time, 3O2, 2Fe2O3, and mole ratio, mole ratio of iron to oxygen was 4 to 3, and these are both in units of moles. So that means for every 4 moles of iron, it's